In this video, we're going to do section 1.4, solving differential equations numerically. The last problem, 1.18, distance with damping. A mass is subject to a damping force proportional to its velocity, which means that the equation of motion takes the form of x double prime is equal to negative ax prime, where a is some constant. If the initial speed is 2 meters per second, and if the a is equal to 1 over seconds, how far has a mass traveled at 1 second, 10 seconds, 100 seconds? You should find that the distance approaches a limiting value. Now assume that the mass is subject to a damping force proportional to the square of its velocity, which means that the equation of motion now takes the form x double prime is equal to negative a x prime squared, where a is some constant, if the initial speed is 2 meters per second, and if a is equal to 1 over meters. How far has the mass traveled at 1 second, 10 seconds, 100 seconds? How about for some larger powers of 10? You should find that the distance keeps growing, but slowly, like the log of t. The results for these two forms of the damping are consistent with the results of problem 1.5. Okay, first when we start out, we'll just know that we have different dimensions for these a's, and all these a's are doing is keeping the dimensions on both sides equal. So if you had questions, that was it. So let's first start with what we were given, and that is the equation. We'll always start with the equation first. S double prime is equal to negative a x prime, where a equals 1. Okay, so now we have that the x prime of 0, or we can think of this as a v of 0 later, is equal to 2, right? And then we have that we're going to make this x of 0 is going to be equal to 0. This is not given, but for simplicity, we want to find the distance it travels, right? So that's going to be the final position minus the initial position. So then it'll just be easier if you set the initial position to 0, right? Okay, so it's easier to turn this second order into two first orders, so we're gonna do that first. Just because it's easier to integrate and do stuff with it later, because it's just simpler. So we're gonna make v equals x prime. This is pretty standard in physics and in other stuff, where v is velocity, right? X is position. So we have v prime is equal to negative av. And then we know that a equals 1 from our given section. So we have now that v prime is equal to negative v. And we can write v prime as dv over dt. And then move it around. So we have dv over v is equal to negative dt. And now we're going to integrate this. So then, integrate 1 over v. So we have ln of absolute value of e is equal to negative t plus some constant c. Okay, now put everything to the power of e. So now we have v of t is equal to a e of negative t. And then keep in mind that v of 0 equals 2, right? From our previous given statements too. So then once we plug in v of 0 and equate that to 2, we have that a equals 2. So now we have v of t is equal to 2 e to the power of negative t. But that's not what we want to find, right? We want to find the distance it travels. But then we remember that v is just x prime, right? So we can write that x prime is equal to 2 e to the power of negative t. Do the same exact steps basically. Dx over dt is equal to 2 e to the negative t. Now just move the dt over, then integrate again. And then you'll see that we get that x of t is equal to negative 2 e to the negative t plus c. And now we're going to use our initial condition once again. So x of 0 is going to be 0, right? From the statement that we defined earlier. And then we get that c equals 2. So we have x of t is equal to 2 minus 2e to the negative t. Okay, so now let's just look at our values for all the t's, and we're just going to do this on Desmos. Okay, so I'm just going to write our f of x, which is 2 minus 2e to the negative x. So keep in mind that I'm just doing that instead of x of t just so for Desmos, but it's the same thing. It's just a function, right? So look at all these values. I'm just going to add a little more just so you can see. But yeah, it looks like they're all approaching 2 about, right? So now let's try to mathematically find them because we know that f of like 100 and f of 1000, like, yes, it might seem like they're all 2, but we know that they're not the exact same value, right? So let's try to find them mathematically. So a the x of t will have a finite distance is if you have t for a very, very long time, all equate to have like one value, right? This means that every increment just adds kind of an insignificant amount of distance where it can just all be put into one thing. So in mathematical notation, that'd be the limit as t goes to infinity of x of t is equal to c, some constant, right? So then c would be the limit distance. So let's just take the limit of x of t, which is 2, 1 minus e to the negative t. So the only thing with that has dependence on t is e to the negative t, right? And that is just 1 over e to the t. So then if you put e to the like infinity or like a really, really large number, that's going to be very, very large, right? But if you do 1 over that number, that's 1 over a very large number, which is basically 0. So that's why we can just make this 2 times 1 minus 0, which is 2 times 1. So our c is going to be equal to 2, so our limiting distance is 2 meters. Okay, so now let's move on to part B, and this is hint. It will follow the same or about the same steps, well, definitely the same process as part A. So if you want to check that one out, see if you understand it, and then try to do this one on your own, I'd highly recommend that. But anyway, we start with our function, of course. So we have x double prime is equal to negative a x squared. And we have the same initial conditions. So then we'll have that x prime is equal to v again, right? Just like we did before. So this time we have v prime is equal to negative v squared, right? Instead of just negative v. We're going to split out again. V prime becomes dv over dt. We put the same variables together. And then now, instead of ln of v, we get negative 1 over v, right? And this can be easily found using the ni derivative. So we have negative 1 over v is equal to negative t plus c. And then let's just move this around so we can get a proper v of t function. And then, like I stated before, this is all the same initial conditions as part A. So we have that v of 0 equals 2, right? And then we can solve and we get c equals 1/2. And then here, as you can see, I just made it into a simpler form. And now we have v is equal to x prime, which is equal to 2 over 1 plus 2t. And then again, make it dx over dt. And now, same exact thing. Now we integrate that. Now we have x of t is equal to ln 1 plus 2t plus c. And then again, same as our conditions before, x of 0 is going to be equal to 0. And we're just going to put that in. So ln of 1 is 0. So this c is just going to be 0. So we're just going to have x of t is equal to ln of 1 plus 2t. And now let's check out the how this x of t function works in Desmos. Okay, now I'm putting it in, but just know that you could probably do this on your own. Yeah, I messed up the x of t. But anyway, it's just a function, right? So this is just the easiest to put on Desmos. So you see we're going 1, 3, 5, 7, 9. Doesn't seem to be approaching something. And now when you compare that to part A, where when you got to like a high f of x value where of the x or an x of t value with the t, they all kind of are like the same value, right? However, for this one you can see it's like pretty different. Those going slowly, it's going like pretty steadily, and the growth is not insignificant. So now let's just try to find the limiting distance, if there is a finite distance or not. Um, you might know this just from the graph, but let's try to do it mathematically. So we know it'll have a finite distance if the limit as t goes to infinity of x of t approaches a constant c. But let's take a limit of this. So limit as t goes to infinity of ln 1 plus 2t. And we can see that this t is just going to go to infinity and ln just doesn't approach a limiting value for when something goes to when the value goes to infinity. So we'll just have the limit is equal to infinity, meaning that there's no finite distance traveled. So even as you go up to the big values, they'll all give you significant increments of value. This is what they were saying. So just a little bit of analysis. You saw that for like I was inputting powers of 10, right? And then it was just giving me like kind of like about like plus 2 for each. So like Morin said on the problem, it is a slowly growing function, but it is nevertheless a growing function that doesn't have a finite value.